situation being handled on Facebook.
Okay, more. Okay, hello, 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 hello. Okay, okay. People are joining. People are joining. I'm assuming you can hear me. Just let me know. And I'm assuming people can see the board, even if you can't read my hand. Oh, thank you, very much. Appreciate it, Adele. Thank you. Okay, yeah, okay. So listen. So just to be clear again, last Wednesday I totally canceled class, and I said there would be a video posted instead, and there was not. So again, so I apologize for that. There was nothing you could have done to compensate for the canceled class. We will still make all the material on time. That I can tell you. Like if you're worried about your larger education in physics, it will all come out in the wash. I'm always a little bit this way, but I'm more this way right now. But just know again, I had to cancel class Wednesday, and that's happening sometimes. And I said there would be a way that we would compensate, and I didn't. So again, I'm just saying I know that it means if I caused anxiety for you guys looking for something, then I apologize. But also, I want you to know you were looking for like what could you do? There's nothing you can do. I know this is on me, so it's I'm behind, and we'll catch up with you guys. You are just trying to do homework 1, 2, and 3, and I'm trying to catch up with that. And you won't get more homework until we get through them. The one thing, so again, I'm just apologizing as you guys come in. Again, I'm admitting that I'm having some difficulties juggling the teaching thing from home. It will be easier. I mean, I will be better at this once my kid is fully in school. Again, just to be honest, I'm just trying to explain why things get scattered. But I will not, the one thing is, I'm not going to hold you guys responsible for my problems, either in your grade or in your education. I just want to say that again, because you don't know me so well. But so where we are now is like you had this slew of homework that was assigned the first week or second week, 1, 2, and 3. We're still going over them. There's nothing you can do until we go over them. And I know that. The one thing I want to ask though is, and I'll try, the one thing I want to ask is, like I just taught the 1050 class. I'm going to teach you guys now. Tonight I'm going to post the 1050 class and this one. Like the one thing I think I have been doing is posting videos once we make them. Please tonight or tomorrow watch the 1050 class recording, not this one, because I am going to do something different here, and I'm going to ask you both to watch the other class, and that way we're going to make some tracks. So and I'm going to try to change the links so that you can always find the old classes from 203 from the spring if you want to, but I haven't assigned any of them as mandatory yet or anything like that. Just hopefully you can find them, because I know but hopefully you know that these recordings are on that YouTube channel with my name, with Professor Yaverbaum on the name. So again, what I'm going to start doing in a second right now to compensate for my being behind the time. I'm going to go to homework number 3. Oh, I believe we have now done homework 1 and 2. It took us a while, but I believe I've said a lot one way or another about homework 1 and homework 2. I can still answer questions at any time for sure, and I will still accept them as submissions until I tell you otherwise. So don't worry about that. But I believe we've covered the material of homework 1 and homework 2. So now homework 3 is where it starts getting thick, and that's what I'm going to start talking about today. But again, honestly, actually, I already did start talking about it in the 1050 class. So please watch that lecture tonight. You won't need it for what we're going to do right now. But right now I'm going to skip to homework 3. I'm going to skip to the problem in homework 3. And again, stop me if this does not make sense, but I'm going to skip straight to a problem that can be done first. I'm going to skip, sorry. I'm going to skip straight. Again, we're on homework problem. We're on homework sheet number 3 called average I think it's number 3, but it's the one called average acceleration by Martins, Yaverbaum, and Bean. And I'm going to skip all the way to problem number 6 called averages and midpoints. Again, I'm going to do that because we can. Excuse me. I'm going to skip to number 6, averages and midpoints. I went over some of the other ones in the other class of 1050. Please watch that tonight. Again, you won't get any new assignment other than that, but all right. So in a second, if this is at all clear, I'm going to go to problem 6 in homework 3. Sorry. So we're going to this problem about averages. I forget what it's called. Yeah, we're going to problem 6, which is called averages and midpoints. Sorry. And this problem is supposedly it's just about averages of numbers. It doesn't seem like it has anything to do with physics. It's like any other problem in physics where you just want to take it on faith and do what you're being asked to do and don't overthink why you're being asked to do it, or kind of like and that's what we're going to do. But in fact, believe me, it does. The idea is that when we get to the end, we see what it has to do with physics, and it really does have something to do with physics. Well, just note, like sailing into this problem, this problem that we're about to do, again, it's number 6 on homework 3, but it could have been homework problem number 1 on homework sheet number 3. Like what we're about to do, we don't need the other problems on the sheet to have done first. The reason we're doing it is because the big takeaway of homework 2, was that we should all not confuse average velocity with average of velocities. Like an almost obnoxious lesson. It really is almost obnoxious the way I taught it. That we have the at least 2 problems in homework number 2 where we're asked something about average velocity, and if one just averages a couple of velocities as one thinks would be reasonable, then one gets the wrong answer. That was the point of homework number 2, is that you can't just average velocities to get average velocity, right? The definition of average velocity is displacement per time. The definition of average velocity is not the average of some 2 velocities. Now, that's an important lesson. But physics would be really annoying. I mean, physics maybe is really annoying, but people would really hate physics and stop doing it if that was the end of that lesson. Like I cannot just, and I actually thought it was when I did this in college or whatever. Like I am saying to you guys, please understand the difference between a definition and a recognition. Understand the difference between a triple equal sign and a double equal sign. Average velocity is not defined to be average of velocities, but for all of you, if I'm just going to say that and leave it, then that's obnoxious, because why are we using the word average then? Like, why am I calling it average velocity if it has nothing to do with the average of velocities? What I was really trying to say last week, and it is an important lesson, is that it has everything to do with it. It's called average velocity for a reason, that the average velocity is like the average of velocities. It really is an average in the ultimate sense of average, meaning the one number that represents a whole. But it just means that, but we were just saying on last week is that the method for getting that average, we have to be very careful sometimes, because truthfully, what it is a weighted average. It's an average that's taking into account all the factors that averages always do. And often with averages, you can't just average 2 things to get the average. Often there's a lot of numbers being averaged. So I want to show you now exactly how average velocity does have to do with averages. Like that's the point of this problem. So all right, so what we're going to do now is show an important, and honestly, again, also, it's not just English. We're going to develop a new equation that we don't have yet from this. So we look at these lists of numbers. So again, I'm in problem number 6 of homework number 3. I look at the numbers. And this is meant to be like a discussion thing, but I think you've already thought about it. I think you thought about it like a week ago, so I just want to get to the point. It asks me to get the average. So I'm looking at, and again, please stop me if what I'm doing is not clear in any way, or if you want me to go back a page. But I'm looking at number 6 from homework 3. Right, and first it gives me this list of numbers: 1, 2, 3, 4, 5, 6, 7, and asks me to get the average. Okay, and I'm going to assume that. Can I just get a show of hands from anybody who knows where we are? Like, if you know what I'm talking about right now, if you understand that I'm going over homework number 3, problem 6, just because it's been so long and I'm so scattered. I just want to make sure. Could you just give me electronic hands or something that you are following? Thank you, Devin. I totally appreciate it. And thank you, Ardell. Oh, and I said Adele before. I meant Ardell. I'm sorry. Thank you very much. And thank you, Melissa. Okay, awesome. That's it. Oh, and 2 part. Thank you. Okay. So this is what I'm doing. And it says, oh, and it says, just into the meeting. Okay. So it asks me for the average, and this is like anything else in physics. If you think you can do a question, just do it. Like if you think it's too easy and it might be a trick, it's probably not a trick. It's trying to make a point. Okay, so I'm asked to get the average of all these numbers. So I'm gonna, if I do it, someone's in the waiting room. So, oh, I thought I just did. So I'm going to get the average of all these numbers in the customary way that people are used to, right? It turns out there's a lot of different ways to get an average. But one way that you all know is, and by average, I do mean, but whenever it's saying average here, I do mean what is the mean. That's what we're being asked. Okay, so the easiest way I can do it, and I know all of you did, I'm sure people did this, I can just add up all the numbers. And then divide by the number of numbers, which is 7, right? And if I add up all the numbers, I believe I'll get 28. And if I divide by 7, I get 4. Yeah. Okay, no big deal. It wasn't supposed to be a trick. I'm just saying, if you got that the answer, again, this is number 6 from homework 3. If you got that the answer was 4, you're totally right. If you got it some other way, you're still right. Okay, the answer is 4. And to cut to the chase with the others, with the others, you can get the answer to all the others the exact same way each time. You can add up all the numbers and divide by the number of numbers, right? So on the second one, you will get 7. On the third one, you will get 9. You will get 9. On the fourth one, now on the fourth one, well, I actually don't remember offhand. Someone could, oh, wait, yeah, oh, yes, yes, I do. Yeah, and on the fourth one, you get 27, sorry. On the fifth one, yeah, it's like a trick, but on that one, you should get 11, I believe. Stop me if I'm wrong. And on the sixth one, you actually have to, the sixth one is 85, 110, 126, 120, 135, 130, 140 divided by 7. I think you get 20. I think someone better tell me from now. Is that right? Yes. Okay. Now here's my point. If you just do, so the answer to A is those answers that I just circled. But then B is the real issue of this. B asks, like, how did one of those lists differ from any of the others? Let me, okay, just to be clear, if I'm being asked to get the mean, the arithmetic mean, the average, then the rule that everybody knows that you use to, get your average exam score, whatever it is, I'm adding up all the numbers and dividing by the number of numbers. Like, that's a rule for getting a mean, and it always works. It always works with all of these lists, right? And technically, it always works when you have a list of numbers to add them all up and divide by the number of numbers. But then what I'm noticing, to answer question B, is, well, while that would always work for all of them, because that is the strict method for arithmetic mean, what's also true, what I noticed, what I'm sure you noticed, for all but the last list, okay, that's ridiculous. I'm trying to write that back because that's ridiculous. What I'm saying that you probably noticed, but it actually really matters. I'm saying that the strict way to get average is you add up all the items and you divide by the number of items. And that will get me the correct answer to every one of those lists. And by the way, if I made an incorrect answer, please let me know. I don't think I did. But there's also a sort of a trick or a pattern that you might have noticed that with most of those lists, with all of those lists, except for the very last one, the result of adding up all the items and dividing by the number of items also was the same result as whatever number was just right smack dab in the middle, at least if the numbers were all arranged in an order. Like once the numbers were put in an order, the middle number was the average number in all cases except for the last list, right? So there's something about average and middle that are related. The average is the middle, exactly, for some of these lists, but not for all. What's the difference? Sorry, so it's waiting. Sorry. Okay, this is the huge point. All of those lists, except for one, had something in common. All of those lists, once you put the numbers in order, the numbers changed by an unchanging amount, right? In all of those lists, like in the first one, it was already arranged in order and each number was one number higher than the last. Same thing in the second list. In the third list, each number was 2 higher than the last. In the third list, the list was generated by adding 5 each time. In the fourth list, it's sort of tricky because it's like not put in order, but you could rearrange numbers in order. Like there's not, if you ever notice that when you're averaging your exam scores, it doesn't matter what order you did the exams in. Addition is commutative. So you can put things in any order to add them. And like on that the fifth list, if you rearrange it, all the numbers are increasing by 2 all the time. It doesn't matter if the numbers are increasing or decreasing, but if they're increasing by the same amount, then it seems that you can avoid the hassles of averaging by simply plucking the number in the middle. That's what I'm saying so far, that adding up all the numbers and dividing by the number of numbers is a tedious process, but it seems unnecessary for all of the lists except the last one. It seems unnecessary as long as the numbers are always changing by an unchanging amount. So hold on one second. One second, I apologize. Okay, I'm saying what we're really saying, and again, remember that So just like triple equal sign is a stronger form of equality, triple equal sign is equal by definition. If with two F's, IFF means if and only if. It's like a stronger version of if numbers change by an unchanging amount. If you have a list of numbers and they change by an amount which stays steady, so they're changing, but they're not changing the way that they're changing, then the mean of those numbers will be the median of those numbers. This is actually an important discovery. Like, this is just about numbers in general, but we're going to apply it to numbers measuring space and time, i.e. physics. I'm just saying what is hopefully staring you in the face from those lists. As long as numbers are getting, my bad. Oh, that's not going to be good. As long as numbers, excuse me for 1 second. Oh, well, I might lose functionality. Pardon me. I'm saying, as long as numbers, look, if numbers are not changing at all, there's no need to average them, right? If you get always a 95 on your exams and your average is a 95, there's nothing to do. If you get different exam scores, then there's a need to average. If every time you get a new exam score, it differs by the same amount, then if you think about it, like if you look at that first list of numbers that we have, that first list of numbers, 1, 2, 3, 4, 5, 6, 7. The point is this: that look at the number 4. Each number. What I'm trying to say is, if each number is the same amount higher than the number before it, then all the numbers above 4 there's the same amount above 4 as there is below 4, because we're always increasing by the same amount. So when numbers are always increasing or decreasing by the same amount, then whatever number lands in the middle is literally in the middle. It's just as far from the lowest as it is from the highest, right? That's not true in the 6th list, because even though that is a pattern of some kind, like those are all the perfect square numbers, at first we increase by 3, then we increase by 5, then we increase by 7, then we increase by 9, etc. So the number in the middle there is not truly in the middle. It's in the middle of that pattern, but there's less numbers below 16. There's less below 16 than there is above 16, because we're growing by more and more each step. So if and only if numbers change by an unchanging amount, then the number in the middle is actually the average of all, meaning even better. Oh, I'm really good. Put another way, okay, and we're going to relate this to velocities in 1 second, but put another way, if you arrange a bunch of numbers, if numbers are actually increasing by a steady amount or decreasing by a steady amount, so they're changing, but they're changing in an unchanging way, if they're doing that, then if you think about it, the number that's in the middle is literally in the middle. It is as far from the lowest as it is from the highest, because numbers are always changing by the same amount. So if you want to get that middle number, instead of adding up all the numbers and dividing by all of them, what you could simply do is average the outer 2 numbers, right? Like if you look at the very first list, notice in the very first list, and my pad is running out of course, my pad is running out of juice. Hold on a second. But in the very first list, I'm saying, if you add up all the numbers and divide by all of the numbers, if you add up all the numbers and divide by 7, you get 4. That's strictly speaking how to get the arithmetic mean, right? If you add up all the numbers and divide by 4. But another way you could just get it is by literally looking at the number right in the middle after arranging them all in order, and you see 4. But another way you can get that 4, when it's all consistent and it's all not a coincidence, is you could actually just average 1 and 7, like the first number and the last number. You can add them together and divide by 2, right? I'm just literally averaging the first and last number and dividing by 2 and getting 4, because all the stuff in between, like any number on the left side that I missed, is perfectly compensated for by any number on the right side that I missed. Like the number right after 4 is 1 more than 4, 5. Well, that's compensated for by the number right before 4, 3, because it's 1. This all works as long as the numbers are increasing or decreasing in a constant rate, which sort of sounds like physics, right? So I'm saying this actually. How can I gotta, my board is, well, okay, because I know this board is about to, the board is about to die possibly. But there's a key punchline coming here. So let me read this just in case, and then say that. So I'm saying the average, so far we have this concept of average velocity defined to be displacement per time. Big lesson of last week was average velocity does not mean the same thing as just average 2 velocities. But now I'm saying, if we look at the numbers and how numbers work, then I am going to say, for a given time interval, for some time interval that we might look at in physics, the average of all velocities, the average velocity for that time interval, indeed will be the same as the middle velocity. It will. The average velocity for something will be the same as the middle velocity, which will in turn be the same as the average of the min and max velocity. So this is about to be a big shortcut we're about to get. I'm saying, oh, if you want to get the average velocity for a whole interval, you could do a shortcut and just pluck that middle velocity. Or even so, you could, or even better, you can do a shortcut and just take the first and last velocities, assuming you know them, and just average them together. And you'll get the average velocity for the whole thing. In other words, you can do what I said last week you couldn't. You can, if and only if the velocity is changing in a, well, by a constant amount. So now I'm saying velocities do work like regular numbers. They actually do. An average velocity will be the average of velocities, but an average velocity will even be the middle velocity, or will be the average of two extreme velocities if and only if velocities in question are doing the thing that the numbers right here in front of us are doing. That is, if everything always moved the same speed, there'd be no hard difficulty to physics, right? I mean, physics is about where's something going to be when. So we use speeds to predict where things are going to be. If everything was always going the same speed, there wouldn't be much of an issue. Things can actually change their speed. They can change their velocity. And that's when we start having to use averages and do fancy things. What I'm saying now, based on the numbers in this example, is if velocity changes in a constant way, if you keep adding the same amount of your velocity to some motion, then doing averages is nice and easy, just like on the piece of paper. If velocities are changing, but in an unchanging way, we'll be okay. If they're not changing at all, there's nothing to do. There's no need for physics. If they're changing in a changing way, things might be complicated. But if they're changing in an unchanging way, we have some tricks at our disposal based on this problem. So let me be even more, and that's what I'm saying here. So let me be even more specific. I'm saying a new equation, we're going to say from now on. Well, I'm saying let because I'm defining something. I'm going to define A with a bar over it to be so I'm going to say, just like we defined average velocity, first we defined V with a bar over it, and we never yet actually defined V without a bar yet. We're about to. We're going to do the same thing here. We're going to say, okay, average velocity is change in position per time. It's like displacement per time. Average acceleration we're now going to define to be change in velocity. Whatever the velocity numbers are, if they change per time, we're going to call that acceleration. But literally, if the velocity changes from one value at one point in time to another value at another point in time, from one point in time to another point in time, we're going to call that average acceleration. So note, I now have two V's. I'm about to have to introduce another equation. Just to make the equate that equation is a definition, by the way, what I just said. So wait, so sorry, let me make this clear. Sorry. So that equation says, and it is new technically in this class. Like, I mean, even if you've seen it before in life, it's new now as of this moment. Okay, just like, remember, average velocity was displacement per time, which is the same thing as change in position per time, because displacement is change in position, right? Similarly, average acceleration is going to be change in velocity per time. how you change the value of your velocity from one moment in time, one instant in time, to another. Notice though those v, so I'm saying average acceleration is defined to be change in velocity per time. Notice change in velocity. Those v's mean velocity, but those v's don't have bars over them. I've never written anything yet with v's that don't have bars over them. I've written some equations with v's with bars in them. So now that must mean that I'm introducing something else here tacitly, and I am. So I'm saying v without a bar does not mean the same thing as v with a bar. V with a bar means average velocity. V without a bar, and this is really the expansion of this is what I did in the other lecture, so please watch tonight. But I'm saying v without a bar and again, like there's the first time I'm saying this in this class, and maybe it's come up in lab or in the work, but from now on, if you see v with no bar, then it means velocity at a moment, at an instant. So v bar means average velocity between 2 points in time. Like anything with a bar, remember between. Okay, v with a bar is average velocity. That means value of velocity between 2 points in time, and it's one number that represents a whole change of quantity. V without a bar over it means velocity at some moment in time, at some point, which actually is a much harder thing. In fact, it's technically impossible to actually observe with your own eyes or even with an instrument. We actually can't, well, and this is the point of the other lecture, but you can't actually see or measure or how fast you're going at some moment any more than you can see how fast something's going in the photograph of some moment, right? In some moment, you don't go anywhere, so you can't have any rate. But, but we can picture it. We can mathematically figure out how fast you're going at a moment by taking average velocity to its limit. So if average velocity is this is the point of the lecture I gave this morning that I want you to watch tonight, please, when it's posted. But in short, how fast you're going at a moment is v without a bar on top of it. What does it equal to? It equals v bar taken to the limit. How fast you're going right now is really how fast you were going for the last half hour. It's the concept of how far did you get in a certain amount of time, but when we shrink that amount of time as close as we can to zero. Again, you watch that in the other lecture. So what I'm saying here is you can change your velocity from moment to moment. You can speed up or slow down, or even change your direction. If you do any of those things, we call that acceleration. Like, average acceleration is your change in instantaneous velocity per time. Instantaneous velocity is something you have at a moment in time. Just like average velocity is changing position per time. From moment to moment, you change where you are, call that velocity. If from moment to moment you change how fast you're going, we call that acceleration. How does this all tie together? What am I saying? I'm saying then, this is huge. I'm going to write this in more. I'm going to write this again a number of times in a number of different ways, but I've just given you two new equations. I'm going to summarize them all in a second, like on one sheet, I'll put them all. But I just gave you the new equation of A bar equals V minus V naught over T. Like the new equation is average acceleration is defined to be change in velocity per time. Now, what I'm saying is, and remember something, remember, even though I just defined A right now for the first time, remember we said if we have any kind of variable and we put it sub 0, that means the value of that variable at t equals 0, right? So by A sub 0, I mean the value of acceleration at t equals 0. I don't know what that value is. I don't even know what example I'm talking about, but I'm saying if I say if A equals A sub 0, that's a physics way of saying if acceleration stays the same value the whole time, right? This expression here means, that's just a fancy way of saying if A is constant, if whatever value it had at the beginning is the same as the value it has at every single moment. Okay, so whenever we say something equals something sub 0, that's our way of saying that that value is constant. If A is constant, if A is constant, if A is constant, that means there's a change in velocity, but not a change in the change. This is very important. I'm going to say it again. Like if velocity is changing at all, if I was going slow and now I'm going fast, then we call that an acceleration. But there's a way, so an acceleration is a change in velocity. But just because you have an acceleration doesn't mean the acceleration has to change, right? Like those lists of numbers, there was a list. The numbers were changing every moment. First it was number 1, then it was number 3, then it was number 5, then it was number 7, whatever. So the numbers are changing, but the way they were changing was always the same. It was always adding by 2. You can imagine velocity, hopefully we can imagine velocities doing something similar. Like if I'm going 10 miles an hour now, but then 1 minute later I'm going 20 miles an hour, and 1 minute later I'm going 30 miles an hour, and 1 minute later I'm going 40 miles an hour, then I'm accelerating, I'm changing my velocity, I'm changing my miles per hour, but I'm changing it by the same amount each time, 10 miles an hour, right? What I'm saying here, and this is a new equation, this is very important, again, I'm going to contrast it with the other equations in a second, but I'm saying average velocity does not mean the same thing as average of velocities. Average velocity, triple equal sign, x over t. But as long as velocities are changing in a constant way, then the average velocity will be the average of velocities. Like the thing that we couldn't do in the Hill figure problem last week, the thing that I'm warning against in homework number 2 is something that you sometimes can do if you're very careful. I'm saying as long, oh, I just lost my board. Okay, well, that's actually a real problem. I'm gonna, all right, excuse me for a second, I'm gonna plug it in and keep talking about it. Hold on. Okay. What I'm saying in English here, how am I going to write? Okay, well, what I'm saying in English here is average velocity is defined to be displacement per time. Average velocity is also the average of velocities. You can get average velocity by doing the average of velocities if and only if velocity is changing in a constant way, if acceleration is constant. I want to write this down in equation form for you. Oh, I just lost it. Right. Okay. Hold on. Let me pause for a second and see if there's a way I can do this. Okay, I don't think there's. So my board is going to just recharge for a few minutes, and then I'll reintroduce the board. But in the moment, what I'm going to do right now, I think the most useful thing I can do right now, since I don't have a board, is I'm going to back up. And I hope people can bear with me. I'm going to out loud say answers to the question. I'm going to go. I'm trying to tell you all a concept that's important from homework number 3. And I did just give you the equation that I want. The key equation that I wanted to give everybody is V bar. Sorry. I did just give you the knowledge that I want to give you. But now, since I don't have a board for the moment, what I'm going to do is start from the top of homework 3, and I'm going to literally say answers. And you can definitely stop me and ask questions, but I'm just going to try to say them now so that we are together so you can see if you're doing things right or whatever. And again, because I don't have a board. Okay, so I'm looking at the top of homework 3. Could someone just raise hand to acknowledge? I'm going to start from the top of homework 3 and just like read answers and try to say explanations as quickly as I can. Thank you, Ardell. I love it. I appreciate it. Okay, so that's what I'm going to do. Hold on, let me just get it back again. Then thank you, Rachel. I totally appreciate it. All right, so I'm top of homework 3, as I say, and you can stop me. I'm not trying to go fast or anything. I'm just trying to do this in a clear way since I don't have a board. But all right, very quick review. And this is all right. So this is review, trying to get straight direction and stuff. So she lives 700 miles north of the city room. She goes, I don't even know. All right, and we're assuming, by the way, assume for this problem like that we're calling north positive and south negative. We do have to make a decision somewhere. You could do it either way, but let's assume that. All right, so the total distance for the journey A is 700 miles. So the answer to 1A is 700 miles. 1B, total displacement. If she's going from Berlin to Rome, and if we're calling south negative, then B, negative 700 miles is the displacement. Okay, if we're calling south negative. C, what's the average speed for this journey? Is 700 divided by 4 miles per hour. You could literally leave it like that, or you could say 175 miles per hour. That's the average speed. So 1C, the answer is 175 miles per hour is the average speed. What's the average velocity? Negative 175 miles per hour. Right. Okay. So that's number 1. You can stop me if there's any questions on that. Now, number 2, and this I sort of talk about in the other lecture that I'm posting tonight, but number 2, now here we have computing instantaneous velocity. By instantaneous velocity, all you have to know here for this question is we mean velocity at an instant. It's true, as of the time I assigned this homework and as of right now, we don't actually technically have any kind of method for that. But as long as we know what it means, we might not be able to figure out a method for all time, but as long as we know what it means, we could often figure out a method for whatever situation we're in. And by the way, that's also why triple equal signs are so important. As long as you have definitions of things, you can figure out equations. That's where they come from, and that's why we believe them. But sorry. So for this one, where to go? What's the instant? It asks the instantaneous velocity at this very precise thing at the 18th minute, 42nd second. It sounds like outrageous. It sounds like you have to do all this math, but you don't, and it's not a trick. What it's really getting at is, on the one, and I wish I were writing this down, but on the one hand, I want to make it clear: instantaneous velocity, how fast something's going at a moment. That is not the same thing as average, right? Just like if you take 85 exams in this class, God forbid, and of course you totally will not, but say you do like 30 homeworks in this class, right? If I say your homework average is a 95, and then I ask, what did you get on the 4th homework? You don't necessarily know, right? Like nobody knows automatically what they got on one individual thing if all they know is the average for all things. However, if you also know something about the context, if you have a rule for how things are changing or not, then you're set, right? Like the simplest case is this example here, where it's asking you for velocity at this obscure moment, like the 18th minute, 42nd second. There's no way you could know that. But you can know your average velocity for the whole thing, right? Your average velocity for this whole thing, you can always know. In this case, it's 40 miles divided by 30 minutes. So that's 40 miles divided by a half hour. That's 80 miles per hour. You can automatically definitely know that your average velocity for this problem, I'm doing problem number 2 on homework 3, problem number 2 on homework 3, your average velocity is, I hope clearly, 80 miles per hour. Like, you know, that's the first thing I would always compute, because it's something I can get is the average. I can just divide displacement, 40 miles, by time, half of an hour. So 40 divided by half is 80 miles per hour. That's my average. That's all I know at the moment. But then when it says my velocity is constant, v equals v naught, so to speak, then I know that I never changed at all. So whatever I once am doing, I'm always doing. So then I must always be doing that average, right? If you got the same score on every single exam and your average is a 95, then you definitely got a 95 on the 3rd exam, as well as the 7th, as well as the 8th, because you always got the same thing. So the answer to question 2 on homework 3, the answer is 80 miles per hour. But just please understand that we know that because we got the average and we had a rule for how the change was occurring. And the rule was the change was not occurring at all. It was, we were losing or gaining no velocity every moment. So now we go to question 3. Okay, and again, this is more carefully done out in the other lecture if you can watch. But in question 3, what we're getting at now is, okay, let's say that you are actually changing your velocity every moment. If you're actually changing your velocity every moment, then it might be a lot more difficult to compute. Then you can't just say, oh, there's no change, so the average is the same as whatever I'm doing every moment. But as long as you know how it's changing, it comes to the same thing. As long as, and that's what this is saying here. If you know, well, and again, this is posted in the other lecture. I'm just going to let my board warm up a little bit more. But so here, the definition of average acceleration is change in instantaneous velocity per time. Okay, so that's how much time it takes you to get from one velocity to another. And each velocity itself is measured in time. So the answer to question 3, part A, when it says expressed in miles per hour per minute, what's the average acceleration of my Toyota? The answer is 30 miles per hour per minute. Let me just say that again. Like, the answer to question 3, part A, is 30 miles per hour per minute. It's not meant to be a trick. It's not meant to be a ton of work. It's meant actually to show, and it is meant to be an answer that has 2 distinct units of time captured as part of that answer. Hours and minutes. That is okay. It is not wrong. I mean, we then ask question B so that we can express it a different way if you like that better. But what we're trying to say in part A is the answer is 30 miles per hour per minute. Both the hour and the minute are both in the denominator of the answer. What does it mean? It means every minute on average, I'm gaining a speed of 30 miles per hour, right? There's 2 units of time because 1 unit of time goes into the concept of the velocity itself. And the other is how much time it's taken me to gain or lose that velocity. So it's 30 miles per hour per minute, totally legit. But then I can convert, and if I convert, and this again, I show in the other lecture, please, and I can't write down right now, but if I convert both of those time units into seconds, which I totally can do so that they're all in seconds, I can do this. It can make it more simple to write in some ways, but it can also make it harder to relate to. They're both correct. But if I convert each minute to seconds and the hours also to seconds, so I end up dividing by 60 and dividing by 3,600, I end up getting an answer that I think is 1.39 times 10 to the negative 4th miles per second squared. I'll just say that again. Again, it's in the lecture that I'll post tonight, but the answer to question 3B to 3b. I believe, and please correct me if you think this is wrong, but I believe the answer is 1.39 times 10 to the negative fourth miles per second squared. And of course, if you've done physics at all in high school, then you might not be surprised to see this unit, but it is surprising the first time you see it. I am saying that the answer to B is expressed in miles per second. Oh, it says per second per second. That is, both the seconds are in the denominator. It's seconds times seconds. So you can abbreviate that and write it as miles per second squared. That looks very strange the first time you see it. It doesn't mean that we're squaring time or doing some weird Michael J. Fox flux capacitor thing. Like we're not doing anything weird to time. We're just saying that the unit of time is being compared to twice, one for velocity itself and one for the amount of time it took to change velocity. So you could say miles per hour per minute or miles per second per second. You get different numbers each way. Either one is fine. It's more traditional to write miles per second squared, as long as you know what it means, but it doesn't necessarily make it easier to relate to. Okay, let me see if the board, but that's question 3. Again, I'll explain that in more detail. I do explain that in more detail to the lecture I did an hour ago. That helps, but if that's good enough for you, that's good. Yeah, but now I'm gonna go on to question 4, and I'm gonna try to grab the board in a second. But what question 4 is getting at now is, notice that acceleration, from here on in, we are defining average acceleration to mean change in instantaneous velocity per time. Average acceleration is change in velocity per time. Velocities were already vector quantities. Like velocity was displacement per time. That is, velocity takes into account direction. Velocities can be negative or positive. So changes in velocity can be negative or positive, and that can get subtle, and that's what the next 2 questions are trying to get at. Yeah, all right, so I'm gonna try to say the answers to this question 4. I'm gonna just try to say them again before messing with the board. Are we still okay? Can I just get, are we still sort of okay? I mean, I know this is definitely not interesting, but is this sort of clear what's happening? Thank you, are the best. You're the best. All right, thank you. I'll take that as, all right. And I'm gonna try this one more without the board, and then I'll try to get the board back. Where did I just go? Sorry. Okay, so I'm doing 4. And I'll even give you everybody the summary now of 4. The real thing of 4 is, because negative signs really matter, like we are still living in one dimension here in physics. We're still, every kind of motion that we're talking about is still as though it's a little mosquito that can go back and forth on the edge of a ruler. Like literally, we can go back and forth on some line. You can call it north and south, you can call it east and west, you can call it left and right, but all we have in our world right now is back or forth in some line of space that we live in. Like we're a little dot in that line, and there's a clock that's always ticking. So there's like time occupying one axis, and there's space occupying one axis. That's what we're assuming here, and we're going to build from that. But in that axis, negative means one direction, positive means the other. So we now have this definition. Average acceleration means change in velocity per time. Velocities could be negative or positive. So a change could be negative or positive. I'm going to tell you right now the summary, that the big point of question 4 and question 5 is that accelerations can be negative or positive, but negative acceleration does not always mean slowing down. Negative acceleration does not necessarily mean slowing down. Like that's what we want to get at here in this question. It could be slowing down while you're moving in a positive direction, or it could be speeding up while you're moving in a negative direction. And by negative direction, I just mean south or left or back, whatever is the opposite of forward, right? Well, let's see the numbers. All right, so we've got this Audi that's driving a certain direction. We've got this Buick that's driving a certain direction. We've got this Camry that's driving another direction, like A, B, C. Okay, and they're driving in different directions and different speeds. And there's a dirt bike, which begins with D. Now, as we always should do at the beginning of every physics problem, like physics problem starts off with a bunch of facts, but there are certain things that are not absolute facts in the world. and this is the whole point of all the train of thought and all that stuff, is there's no objective zero place in the world. There's no objective zero speed in the world. So what we do is we pick a zero and we just are going to say what's positive and what's negative, right? We can say whatever we want because the laws of physics hold the same in all unaccelerated coordinate systems. But whatever we choose, we have to be consistent with and know what we chose. Okay, so for A, I'm choosing, and again, I would draw this. This is the first way I begin every physics problem, whether I'm told to or not. If I'm solving a physics problem, I always, and I really mean this, by the way, I really always choose a coordinate system before I start, even if I think the problem's easy, but especially if I think I don't know what I'm doing, I always choose a coordinate system first. And so in this case, what that means is choosing to say that east is what I'm going to call positive from now on. I would like just draw, a coordinate grid on my piece of paper right now, but I'm going to say that anything going east will be positive, and therefore anything going west will be negative. That means any displacement, any velocity, any acceleration, anything that goes west is going to be negative. Anything that goes east is going to be positive. That's my choice for part A. You can do the opposite, but you just have to then be consistent with yourself. So for 4A, I'm saying east is positive. All right. Then, given that choice, it says write down the initial and final velocity of each vehicle using positive and negative signs. Okay, all right, that's cool. Well, this is actually hard. Oh no, sorry. Okay. So given the choice you made in part A, write down the initial velocity final of each vehicle. I do assume they all started off at rest. I think I apologize. I think this problem, which my very good friend and colleague, Professor Bean wrote, we don't technically actually know the initial velocity. It should have said that the initial velocity is at rest, is zero. Somehow, yeah, assume, unless otherwise told, that the beginning velocity of each one is at rest, is zero. So for example, the Audi began at velocity 0 and it ended at an instantaneous velocity of 50 meters per second. The Buick, I assume, started at 0. By the end, it was going 50 meters per second, but in a different direction. The Camry started. Oh, my God, I'm so sorry. This is what comes of not writing things down. Forget the 0 thing. The problem is clear. The problem is clear. It says driving east at 10 meters per second, speeding up to 50 meters per second. So I'm sorry, I'm still on 4B here. The initial velocity of the Audi is 10 meters per second, positive. The final velocity of the Audi is 50 meters per second, positive. Like, why positive? Because they're both going in the east direction. The Buick, I'm still on question 4B. The Buick is initially going negative 10 meters per second, because it's 10 meters per second to the east. And then its final velocity is 50 meters per second to the west, both negative. I'm gonna pause a second to get my board because it's driving me crazy not writing these things down. Pardon me. All right, I apologize. We're gonna see if we can survive on 10% charge here. Pardon me for a second. I'll keep reading while the thing is turning on. Then the Camry, its initial velocity is positive 50 meters per second. Its final velocity is positive 10 meters per second. The dirt bike, it starts at negative 50 and ends up at negative 10. Okay, those are the initial and final velocities of each one. I'm going to try to write them down for you in a second, but notice each number I just gave you, even when I gave you an erroneous number, each number is an instantaneous velocity. Like, the question says initial or final. Initial means at moment one, final means at moment last, but those are just sub cases, specific examples of instantaneous velocities. They mean velocities at various different instants. So all of the V's that I just read out loud as answers are all just V with no bar on top of the V. They're not averages, they are instantaneous. Okay, my board is coming back to life, we hope, we think. So now to get the average acceleration of each vehicle during the 10 seconds, like in other words, question C of problem 4, I am just going to use this definition, and I am just going to plug in and okay, and here we finally go. Okay. So thank you for your patience. All right, so this is, I'm going to quickly just write these down. All right, now again, we've done this homework out of order. I started with problem number 6, then I went back to 1, 2, and 3. Now I'm doing 4, and I'm just write the answers clearly because I said them so unclearly. And we're going to end in 7 minutes right after this. Okay, so I'm letting East be positive B. Okay, so just to give you an example, so for each vehicle, I'm writing down an instantaneous velocity. So I'm writing down a velocity that does not have a bar over it, but I'm writing like a first and a last. So one way I could write it that will help with the question is like with the Audi, its very first velocity, its initial instantaneous velocity, V sub 0, V naught, was positive 10 meters per second. 10 because I was told that, and positive because we decided that east would be called positive. Its final velocity, which I'm just calling V, is positive 50 meters per second. I could call that those two V sub 1 and V sub 2, or V sub I and V sub F. You can call them whatever two velocities you want, as long as they don't have bars over them, and as long as they're different. So that's the Audi, and I'm just going to continue writing down. Whoop. So the Buick initially is going negative 10, and then it's finally going, it speeds up to negative 50. So notice, even though it's sped up to a negative velocity because both of its velocities were negative because the whole time it was going west. Those negatives just mean it's going west. It's distinguishing it from the Audi, which is going east. The Camry, were initially going positive 50, but it slows down to positive 10. And then the dirt bike was initially going negative 50 and slowed down to a final velocity of negative 10. So if you really think about it, these are sort of the 4 cases, right? You could be speeding up while moving in a positive direction, or you could be slowing down while moving in a positive direction, or you could be slowing down while moving in a positive direction, or slowing down while moving in a negative direction. And what I want you to see, and I know we're going to end in 3 minutes, I mean, these are meant to just be easy plugins, but they're meant to make the point. I should never say easy, comparatively easy. Like if you notice, so the average acceleration of the Audi, is like 50 minus 10 over 10. So that equals 4 meters per second squared, positive, right? It's 50 minus 10 all over 10. That's the Audi. The Buick, we're going to end as soon as we get these 4. The Buick is going negative 50 minus negative 10 all over 10, right? That's negative 4 meters per second squared. And I'm just going to get the last two answers. Let me summarize. And the average acceleration of the Camry, well, it was going positive. It started at positive 50. It ended at positive 10. It did that in 10 seconds. So that's negative 4 meters per second squared. That's the Camry. And the average acceleration, again, this is where we're going to end, of the dirt bike. The average acceleration of the dirt bike is negative 10 minus negative. If you just plug in the numbers carefully and consistently, then there's not meant to be anything too hard about this, and hopefully you get it right. But what it's trying to show, if you plug in the numbers carefully and consistently, notice there's two cases of positive acceleration. Like the Audi is accelerating positively, but the dirt bike is also accelerating positively. If you're traveling in a positive direction, gaining speed, or you're traveling in a negative direction, losing speed, in both cases, you're gaining velocity, because velocity takes into account direction. So if you just think of a bunch of velocities, and I know it's 1:30, so I'm just say this and then that's it. If you think of a bunch of velocities on a long number line with 0 in the middle, a positive acceleration means you're gaining velocities. It means your velocity numbers are going up. So that either means that your your positive velocities are getting more and more positive, or it means your negative velocities are getting less and less negative, right? Moving to the right on the number line means getting farther away from 0 if you're on one side of it, but it means getting closer to 0 if you're on the other side of it. So speeding up in a positive direction is the same thing as slowing down in a negative direction in physics. Negative acceleration. So I guess this is the last thing. This is literally, and then we're going. And then again, don't do anything new except please watch when these videos get posted tonight. Please watch the other class video just to see the things that you didn't get here. I'm writing 2 things. What I just wrote is the summary of what I'm saying in English, and I know it's 1:30. Sorry, and there's someone in there. But the one other thing I just wanted to do I'm just going to write down all the equations we have so far right now. There's not many, but just on as neatly as I can on this one next page, I just want to write down all the equations we have so far so that there's as little confusion as possible to summarize everything from today. And again, don't do anything new. Just please watch the video that gets posted tonight and just keep going wherever you are. If you're caught up, then just wait. You're fine. And I appreciate how everybody's bearing with me. But here's the equations we have so far in this class that I think we know. Stop. Sorry. Okay. Okay, just to summarize what we have so far, and I'm going. We have a definition of average velocity. We have a definition of average acceleration. We have a definition of instantaneous velocity, which is the limit of average velocity, okay? Then we have and just note the thing that we did at the beginning of class today, and I'm writing down now, that last equation, notice it's also for average velocity. The first equation, there's two equations for average velocity. Do not get them confused, please. And do not think that they're a contradiction. One equation is a definition, triple equal sign, the other is not. That means the first equation is always true. It's never wrong. If you ever put it down on a test, you're going to get points for it, even if you don't know what to do next, right? The equation for average velocity is what average velocity always equals by definition. It's never wrong. But then the second definition is true, is something that's true about average velocity. It can help you get average velocity if you're missing other information, but only true if acceleration is a constant. Like that last equation is the only one that has the double equal sign. That actually means that it's not always true. It's only true when acceleration is equal to a constant. When velocity changes, but in an unchanging way, then the average velocity is the average of velocities. Then and only then. That's what we're saying so far. That's a summary of everything today. The last 2 days, you are very patient. Again, don't do anything new except watch a video. If and when it's posted, it'll be posted to, well, I mean, it will, and it'll be posted to my channel at YouTube, which I need a new link for. I apologize, but and I'm catching up on email, and I'm going to go now and let the other people in. I apologize.